We have already discussed three factors due to which we get anomalous values of magnetic moment. The rest of the two factors include equilibrium between two spin state and due to non-equivalent position in the unit cell. First of all, we are considering the factor of when there is equilibrium between two spin states. As you are familiar, if we consider an octahedral complex, then in the octahedral complex D4, D5, D6 and D7 ion can form both type of complex, high spin as well as low spin. And if the complex is formed at a CFSE value at which the high spin and low spin state are in equilibrium, this can be considered by using this Orgel diagram. As you know, you have already studied the Orgel diagram for different ions in your second semester. This is the Orgel diagram for D4 ion. In this diagram, you will find that there is a vertical line between this diagram which shows that before this vertical line, the complex is existing in the high spin state, and beyond this vertical line complex exists in the low spin state. But at this vertical line, if we consider this position that is at the vertical line, the CFSE value when it is equal to this vertical line, then the complex can exist in either of the state, in low spin as well as high spin state. This kind of condition also exists in the D5 ion and also in D6 and D7 ion. So in such ions, when the CFSE value lies along this field where the high spin and low spin state are in equilibrium, then we also get anomalous magnetic moment values. If we consider the nickel 2 positive ion, as far as the nickel 2 positive ion is concerned, in octahedral ligand field, such type of spin state change are not possible. This can be understood with the help of this Orgel diagram. This is the Orgel diagram for a D8 ion, and in this diagram here you will find that this is our ground state term. This is the ground state term, which is triplet A2 term, and this is the first excited state term, which is a singlet E term. You will find that both of these terms are parallel to each other and they are not crossing each other. So there are no chances of changeover from high spin state to low spin state. So such type of changeover are not possible in D8 nickel 2 positive ion. However, in spite of that, we get anomalous magnetic moment value. Actually, the reason for that is, in the case of nickel 2 positive ion, actually the complexes are not perfect octahedral. The complexes are tetragonal in nature, due to the kind of configuration which is possessed by the molecule and due to which the orbitals in octahedral field are further splitted. Now, if the nickel 2 positive ion form weakly tetragonal complexes, then there could be formation of two types of complexes depending upon the relative values of delta 1 and P. Here delta 1 represents the energy gap between the higher energy A1G and B1G orbitals. If delta 1 value is greater than pairing energy, in that condition all the electron will be paired up and thus the complex will be diamagnetic in nature. But if delta 1 value is less than pairing energy, then the complex will be paramagnetic in nature because electron will be distributed one each in A1G and B1G orbital, so there will be two unpaired electrons. So in this case, equilibrium can exist in these two forms. If delta 1 and pairing energies are comparable to each other, in that condition equilibrium can exist. In the case of strongly tetragonal complexes, there is difference in energy state. Energy state जो है वहाँ पे change हो जाती है, and here the nature of complex depends upon the comparison between delta 2 value and pairing energy. Now again, if delta 2 is greater than pairing energy, there will be formation of low spin complex which is diamagnetic in nature, and if it is less than pairing energy, then there will be two unpaired electrons and the complex will be paramagnetic in nature. In either of the case, whether the complex is weakly tetragonal in nature or it is strongly tetragonal in nature, there will be chances of existence of equilibrium between two spin state, and thus we get the anomalous magnetic moment value in this condition also. Beside that, in this complex, that is dichlorido tetrakis N and dash diethyl thiourea nickel 2, it is spin paired below 194 Kelvin and it attains paramagnetism with rise in temperature, which has been shown in this table. When the temperature is less than 194 Kelvin, then expected magnetic moment value is 0 because all the complex exist in low spin state. But as we increase the temperature, you will find that as we are increasing the temperature, there is corresponding increase in the magnetic moment value, because now low spin complex are converted to the high spin form, and the population of the complex in high spin form increases with the rise in temperature, and thus equilibrium constant value also increases. Thus this clearly indicates that there is equilibrium between two spin state in such complexes. So these kind of equilibrium between two spin state can be used to explain the anomalous magnetic moment values of such complexes. The last reason due to which we can get anomalous magnetic moment value is magnetically non-equivalent sites in a unit cell. If we consider a green colored complex, that is dibromido benzyl diphenyl phosphine nickel 2, it shows anomalous magnetic moment of 2.7 Bohr magneton. And X-ray studies have shown that the unit cell contains 3 nickel 2 positive ion. Out of these 3 nickel 2 positive ion, 1 exists in the square planar field, while rest of the 2 exist in tetrahedral field. So due to the non-equivalent site occupancy of nickel 2 positive ion, we are getting this anomalous magnetic value of magnetic moment. Similarly, in the yellow form of Lifshitz complex, that is mesostilbene diamine nickel 2 dichloroacetate 2/3 ethanol 4/3 water, there is anomalous magnetic moment value of 2.58 Bohr magneton. Again in this complex, it is due to non-equivalent occupancy of metal ion in the unit cell. In this case, 2 metal ion exist in the octahedral field while 1 in the square planar field, resulting into an anomalous value of magnetic moment. So these are the various factors on which we can explain the anomalous magnetic moment value in the various cases. In the next lecture, we will be covering the other topic of this unit.